All right, let's begin with the active site again. We started it last time, and I lost recording, so let's go over it again. Remember that chymotrypsin has the two phases, the slow phase and then the fast phase, or the fast phase and then the slow phase, I'm sorry. And so what we have in the first phase is that our substrate, and again, this is our substrate, is the peptide. And our substrate is going to come into the active site, and it's going to anchor there by a hydrophobic amino acid side chain, and this is called the hydrophobic pocket. And what happens is the serine with the hydroxyl group and the histidine with the nitrogen already have a connection with the hydrogen bond. But what happens is that the oxygen on the serine is going to act as a nucleophile to attack the carbon of the carbonyl of our amide bond, of our peptide bond. And so what happens is there's a new covalent bond that's formed between the serine and the substrate, the carbon of the carbonyl. And we get a very strained intermediate. And this intermediate looks like the transition state. So it looks like the transition state for breaking this peptide bond. And it's held together through hydrogen bonding with the histidine. So this intermediate is unstable because the carbon's bound to two electronegative atoms, one being a negative charge. Also, the nitrogen is a little bit more electronegative than the carbon. So what happens is the carbon-nitrogen bond breaks because the electrons on the oxygen, the charged oxygen, are going to fold in and form a double bond, a carbonyl. And then we get this, what kind of bond did I say this was? Carbonyl, oxygen, and then another carbon. An ester. This is an ester bond. All right? And so then we have the cleaved peptide bond where one half of the peptide gets to float away. And the histidine has donated a proton, and the serine acts as a nucleophile. So if it donated a proton, then it acted like an acid, right? It acts like an acid. So then we have this the end of the first phase. Now we know that esters are susceptible to hydrolysis. That means we're going to break up the ester bond using a water molecule. That's what hydrolysis is. So then what happens is a water molecule gets into the active site, and the oxygen attacks the carbon of the carbonyl. This is especially partially positive because it's bound to two oxygens. So we have the electron density away from the carbon. So here you can see that the water is going to come in. This is made even better nucleophile because there's hydrogen bonding between the histidine and one of the hydrogens of the water. So then we get our second tetrahedral intermediate. It's different from the first in that the first had a carbon-nitrogen bond. Here we have the carbon-oxygen bond. So this tetrahedral intermediate, again, the nitrogen picked up or accepted a proton from the water, and the water acted as the nucleophile. Now this intermediate is unstable, again, for the same reasons that the first intermediate are unstable. We have a lot of electronegativity around the carbon. We have, and especially because of this negative charge in the oxygen. So we're going to break the ester bond and then make an acid, and we are left with our active site in the same way. This now has the rest of our peptide has less of an affinity for the active site and can float away. So if we added one more frame, we would just see the active site with nothing in there, ready for another substrate to come in. So we saw two mechanisms here, acid-base catalysis and nucleophilic substitution catalysis. So which one acted as an acid-base catalyst? The serine or the histidine? The histidine, because at first it donated a proton and then it accepted a proton. And which one acted as a nucleophile? The serine, the oxygen, and also the water acted as a nucleophile as well. metals or cofactors in enzymes can also act as catalysts. They can act as a Lewis acid or Lewis bases. Remember, if you don't recall, the definition of a Lewis acid is in terms of electrons, and it's just the opposite of what it would do with a proton. So acids are proton donors or electron acceptors. So that's the way I remember it. So a Lewis acid is an electron pair acceptor. So you can see that this zinc, it's accepting electron pair from the oxygen. So it's acting as an electron pair acceptor. And so we see magnesium, zinc, manganese. They are what we say cofactors in our enzymes. There's a lot of enzymes that need them for activity. This one is carboxypeptidase A that requires zinc in the positive 2 oxidation state for activity. And so we have is imidazole side chains of histidines. And our carboxylate group of a glutamic acid will form some coordinate covalent bonds with the zinc, and then there will be another free one to interact with this this oxygen on the substrate. So this what this is going to do is sort of get this carbon even more ready for nucleophilic attack. It will make it even more positive for nucleophilic attack. We can further classify our enzymes mechanism by specificity. We can have what we call absolute specificity, that there's only one substrate for this enzyme, and it makes a particular product. This is when you have most like the lock and key mechanism for our active site. It's a rigid active site. There's not a lot of changing of spatial changes in the amino acids. You can have relative specificity, where you have a more flexible active site. You have more of an induced fit. It's like chymotrypsin, where we just took a look at. The amino acid that fits in that hydrophobic pocket can be phenylalanine or tyrosine. So that's relative specificity. You can take a couple. Another, which is so cool, is stereospecific enzymes, where one stereoisomer, the left hand, right, will be able to go into the active site rather than the other, or it can give one product, one stereoisomer product rather than the other. So one mirror image rather than the other mirror image. So absolute, it only takes one specific substrate. Relative specificity, it might take a couple. In stereo, that's where it only takes one stereoisomer rather than the other. Or it gives a product that has one mirror image rather than the other. So here, this is an example where if you have what we call an asymmetric binding site at the active site, where it's not sort of symmetrical, where this can only fit in one way, that's where it would be stereospecific. So if you have it where it only can fit in one way, just like expensive gloves, you can imagine that the glove would be the enzyme active site, taking in only the right or the left hand. My gloves aren't like that. I can put them on either hand. I don't spend that much money on gloves. All right. Now, we all know that enzymes provide an alternative pathway to lower the activation energy. That's the purpose of them. And it's to get to transition state easier, and that lowers the activation energy. So we're getting to that transition state, but it's through a different pathway. So that's the function of an enzyme. Now, the transition state looks different than either the substrate or the product, and we often want to know what that true nature is. It's very important that we understand the mechanism, like we understood what was going on with chymotrypsin. We want to know how these different enzymes work. So we want to know what we call the true nature of the transition state. And so what we do is we synthesize what we think, chemicals that we might think that look like what the transition state looks like. So here's a reaction that is catalyzed by an enzyme. The conversion from L-proline to D-proline. So we're going from one stereoisomer to another. And in that mechanism, we think that the transition state is a planar, negatively charged carbon. So it would be a planar molecule. So what they did is they said, okay, this is unstable, so you can't synthesize this and expect it to stay in your beaker. So what they did is they said, okay, let's synthesize a molecule that is stable, that looks like this, and see if it fits into the active site. And it really helps us figure out mechanisms. So I wanted to sort of explain, how do we go about figuring out what exactly is the mechanism in each active site. And this is oftentimes the way we go about it. In preparation for looking at our pathways, starting with glycolysis, we need to really understand cofactors and coenzymes because they're going to be the things that are doing the work for the enzyme. And we're going to pay a lot of attention to them. And so we're going to finish up this chapter by looking at cofactors and coenzymes. And then in chapter 16, we're going to study monosaccharides. But that will fully prepare us after the exam to go into glycolysis. So sometimes people confuse these two, cofactors and coenzymes. They might define them as basically the same thing. But in general, cofactors are going to be the metal that add to the protein. So they're all prosthetic groups. Okay? Cofactors and coenzymes are prosthetic groups. And what I mean by that is they're added to an inactive protein to make them active. They're added to an inactive protein to make them active. So they're prosthetic groups. So they can either be metals or vitamin-derived, sometimes non-vitamin derived, but usually they are. So cofactors are the metals. Coenzymes are organic substances. And that's how we're going to differentiate the two. So if I say it's a cofactor, I'm going to mean that it's a metal atom. And if it's a coenzyme, it's going to be an organic substance, usually derived from vitamins. And we'll talk about that. Let's start out with cofactors. They're often transition metals. Why would transition metals, such as these, serve as good mediators in our reactions? Well, there's a number of things. They have high positive charge density. And what can that do for you? Well, it can pull electron density away from, say, that oxygen that we saw before, that zinc did. It can act as a loose acid, as an accepting electron pairs, maybe in empty d orbitals. It can mediate redox reactions. We are going to spend so much time on this. Iron, copper, they have multiple oxidation states that are stable. Iron has 2 and 3. Which ones do copper have? Copper has, I show you 2, but there's one more. One more. It's copper 1 and 2. Copper 1 and 2. So we can say, we can use these to mediate redox reactions, and we're going to see this quite a bit, where if iron is oxidized, it's iron 3. If it's reduced, accepting an electron, it's iron 2. And it goes back and forth, back and forth. These cofactors will pick up electrons by being reduced and then give them away by being oxidized. So we're going to spend a lot of time talking about this. Again, they polarize water molecules, just like using their high positive charge density. Here I have an example, much like the last one that I showed, where a zinc is going to polarize a water molecule so it can act as a better nucleophile to attack carbon dioxide. And here we showed the mechanism by which this enzyme, carbonic anhydrase, is going to attack, use a water molecule to attack carbon dioxide to make carbonic acid, and furthermore, bicarb. Now, coenzymes, most of them are derived from vitamins. There's two groups. They are either water-soluble or fat-soluble, lipid-soluble. So you can see the vitamin that you're going to look on the side of your processed food, all right, or your milk or whatever you're eating. These are the vitamins that you're going to eat. This is the coenzyme that it produces, and this is the process that it's involved in. We're going to spend a lot of time with TPP, NAD, FAD, coenzyme A. We're going to spend a lot of time looking at how these work in glycolysis, the citric acid cycle, and in the electron transport chain. They're very, very important. So you eat niacin, you get some NAD, and we're going to see exactly how they work. Here you have to be careful with vitamin A, vitamin D, and vitamin E. These are lipid-soluble. That means they can bioaccumulate. It's very hard for you to get rid of them. I remember my freshman year in college, this woman had an eating disorder and would only eat carrots. So what color did she turn? Orange, because her skin, which contains fat, would bioaccumulate vitamin A. It was really scary to see her. She turned orange.
Yeah, like, does that ever go away, or is she just?
Yeah, I think it can go away, but it takes a while. So it's really a problem.
Probably had good eyes.
Yeah, she probably had good eyes, but she turned orange. And there was another girl. I don't know how it is on campuses anymore, but when I was in school, there was 2 girls on my floor my freshman year that had to leave college mid-semester because of eating disorders. Is it that prevalent still? It really is. It still is. That's sad. But these we're going to look at how these work, these lipid-soluble ones. But this is why, guys, you have to be very careful about taking vitamins. You got to make sure that you do it under the direction of a physician. That you're not going to GNC and getting these unregulated vitamins. What was it? Walmart, they were saying it was sawdust, actually, in one of the Walmart vitamin caplets. So it's Wild West. The best way to get your vitamins is food, right? Oh, I wish she was here because she took the nutritional one. Oh.
We'll talk about it on Monday.
Yeah, we're going to have to revisit this on Monday. So she's not. So yeah, it's really important. But this is kind of neat. So kind of when we're talking about these coenzymes, you're like, oh, I need to eat my green leafy vegetables so I can get some. What does green leafy vegetables? Folic acid, right? Iron. Yeah. What else is it? No, your breads are fortified with riboflavin, right? Or niacin. I don't know. We'll have to see. That should be a project. Look at the foods that you eat all day long and see which ones have all these. Like, examine how much you're getting.
I know the cereal will have riboflavin and stuff.
Riboflavin is in cereal?
Yeah.
Yeah. So if you're having a party this weekend, what you could do is take Total, okay? Take Total and make a mush out of it with water, and take a stir bar from one of the labs, and they're white, right, the magnets, and put it into the Total, and when you pull it out, you're going to see lots of little iron flecks, like solid iron. That's what you're eating when you're eating, fortified cereal, iron flecks. So, I don't know. Anyway, I think it's fun. But yeah, this girl turned orange. And vitamin K. That's also lipid soluble.
So the green ones are all soluble?
The green ones are lipid soluble. And these are aqueous.
The blue is aqueous?
The blue is aqueous, yep. So vitamin C, you know that it's silliness to eat a lot of vitamin C. right? The vitamin C pills, because what happens? You did, but you just pass it.
It just goes away, but I was like, hyper.
Oh, you were really hyper? It made you hyper?
I don't know, I just felt like loopy for, yeah, there's a lot of sugar
Oh,
and stuff.
yeah, they have a lot of sugar.
They tasted really good.
I know, it's really hard.
I like ate 5 of them.
There's a lot of sugar in them. Yeah. You wonder about some of these things. Does anybody go to GNC to get their vitamins? Yeah. Just be careful, whatever you do. And the last time I taught this class, there were some bodybuilders in my class, and they were like big GNC proponents. I'm like, that is the Wild West. So you gotta watch it. All right, NAD. We're gonna say that word like 5,000 times the rest of the semester. All right. NAD comes from niacin, and it's involved in redox reactions. So you do not need to know the structure. I'm just showing you here. But it has a nicotinamide ring that's not nicotine, okay? An adenine ring, okay, that's a nitrogenous base, and 2 sugar phosphate groups. So it has the base, the sugar phosphate, sort of like DNA, has the sugar and phosphates. And then this nicotinamide. Now, this nicotinamide is the business part of this molecule. And this is where it is going to do the mediation of the redox reaction in this ring. So oftentimes we are very lazy, and instead of writing the entire molecule out, we'll just do R, right? We talked about that when we did our organic, because we were like, just R, because I'm not going to talk about the rest of it, and I'm not going to draw it all out. So here we're showing this nicotinamide ring, and then we know that there's 2 sugar phosphate groups in that base that's attached to it, but we're not showing it here. So here you can see that there's resonance between this structure and this structure. Whenever you have double bonds, especially double bonds that are conjugated, meaning every other one, think that you can have resonance, meaning that those double bonds can be placed somewhere else. That leads to great stability. So this, starting out, we have the positive on this nitrogen. Well, we can flip around and put that positive on this carbon here, as we show in this, this resonance structure. And when the positive is on the carbon, a hydride, and this is going to be our packets of electron. Hydride is a packet of electron. Mostly when we were looking at our reactions so far when we're dealing with hydrogen, we're looking at acid base. So acid base are proton switching reactions. Redox reactions, we're going to talk about a lot later, they're electron switching reactions. And so here we can see that the hydrogen is being a carrier of an extra electron as a hydride. And that goes on to this carbon with the positive, and then becomes our reduced NADH. So here it's reduced because it has an extra hydrogen. Without the extra hydrogen, it's in its oxidized form, so NAD plus is the oxidized form, and NADH is the reduced form. So I need you to know that the nicotinamide ring is where the action occurs on NAD, and that it will accept a hydride, a packet of electrons, and without the hydride, it is oxidized. With the hydride, it's reduced. These are other coenzymes that are involved in some transfer groups from one molecule to another. They play a role in making bigger molecules and biosynthesis. We're not going to go over those. I just wanted to point them out. Here's an example. The peroxyphosphate coenzyme right here. And this is just an example. We're not going to really see this too much. So if you're going to focus on the action of one coenzyme, look at the NAD. This one is just fun to show. Yes?
So NAD is electron carrier, right?
Yeah, NAD is an electron carrier.
So does it like pair up with an enzyme and then they go together?
NAD is going to be a coenzyme for other enzymes, and we're going to see that.
In that picture, NAD would fit in the active site
Yeah,
of the enzyme,
yeah,
and then it would make like a new active site.
yeah. If you see, oh, right there. So here you have your inactive protein. You're going to then put the cofactor in, and then it activates it. So these things, the metal ions and all these vitamins, they are going to activate your inactive protein, the peptide chain. So I would focus on this NAD rather than this last one, but it's fun to show. So here, the polypeptide chain is E-transaminase. So that's the enzyme. And then this peroxyl phosphate is the coenzyme. So that's what's being bound to this enzyme to make it active. And what it's going to do is it's going to move this nitrogen group from glutamate to the pyruvate in order to make alanine. So what happens is, in this mechanism, is that the nitrogen, the amine group, comes off of the glutamate, goes onto the peroxyl phosphate, as we have here, and then it passes it to the pyruvate and makes alanine. Now, I want to pause right here just for a second and take a look at this sort of reaction here. This might be a new way to look at a reaction. Normally we see it this way, the double arrows mean that it's in equilibrium. But I want you to focus right here. When you see this sort of squiggly arrow, it means that this one is reacting with this one to produce this and this, okay? But the things that are kind of on the sides are like coming in and then going out, not going further in our sort of stepwise look at our reactions in our pathway. So here, the enzyme with the peroxyl phosphate is going to react with a glutamate that has that nitrogen on it, and once it's reacted, it produces alpha-ketoglutarate. That's this molecule here. But it's not going to go forward, right? What's produced is on the peroxyl phosphate, the nitrogen is bound. And that reacts with another pyruvate. So you can see this doesn't have the arrow on it, so it's coming in. And then the alanine is going out. And then we're left with the unbound or free enzyme. So that's just another way to look at the reactions. And we're going to be looking at our pathways. We're going to see it quite a bit. Again, I'm not going to ask you to remember anything about this slide other than there's coenzymes that can hold groups. They're like a middleman in transferring a group. Here in the overall reaction, we're transferring an amine group from glutamate to pyruvate, making alpha-ketoglutarate and alanine. But there's a middleman in this reaction, and the middleman is that coenzyme. So we've seen two ways that coenzymes can work. It can mediate a redox reaction by accepting a hydride or giving out a hydride, or it can be a middleman with the transferring of groups. That's it.